So our next speaker is Professor Hong Im from King Abdullah University of Science and Technology, also called as KAUST.
Okay, good afternoon. Thank you for sticking around till the last talk of the day. My name is Hong Im. I came from Saudi Arabia. So as usual, I know the time is limited, but I would like to spend a few minutes for those who are curious about relatively new school of KAUST. I will give you a brief the introduction to that before I get into the technical part. So the KAUST was founded a little over 10 years ago now, 2009. We opened the campus. We are located on the west side of the Saudi Arabia, the nearby Jeddah. It's about an hour north drive from the Jeddah airport. The campus size is small, but it's roughly 6 kilometers by 6 kilometers. And this is an aerial view of the campus. It's a unique, it's just like, I found a lot of similarity of IIT Kanpur, although our size is much smaller. So we have everything is within the compound. And the people, all the students, faculty, staff live on campus. And the main research and the laboratory buildings are all happening here in the small campus area. We are developing rapidly the industry park, where a lot of companies are moving in to build the bridges from the cutting edge research, translating over to industrial, the practical application. We are a graduate-only program, about 1,000 students, master and PhD, 150 faculty members, and many research scientists and postdocs. Altogether, it's a small city by itself. We have about 7,000 to 8,000 the residents on campus. And what we are really proud of is our community is extremely diverse. So we represent more than 100 countries, literally from all over the world. And that really adds to the more power to the cultural diversity and the research productivity. So just jump into the CCRC. So we have an academic program that confers degrees to the students, and each of the faculty members is affiliated to one of these academic programs. But research-wise, we have also separate research centers, and out of the about dozen centers, CCRC is one of the exemplary centers. We really work as a team. There are 9 full-time faculty members, led by Professor Will Roberts. I heard he came here about 3 years ago. And I'm currently the only modeling computation person. We have 2 engine experts, 2 kinetics experts, and 2 plasma-related application. And recent hire was on the high-pressure diagnostics. So I'm saying this more detail because as a way to give you an opportunity for the students to explore future research opportunities to come to KAUST. We are fairly one of the largest combustion groups in the world. Right, this number is already a little bit outdated. We have about more than 150 members altogether. And as you have seen, we really cover lots of, within the CCRC itself, we also cover more than 30 countries. And our research is highly interdisciplinary and also very synergistic. So in terms of physical scale, we deal with molecular level kinetics all the way to real engine devices. And we do the simulation, and there is a counterpart experimental facilities. And we really need more faculty members working on the simulation components of all these multidisciplinary combustion problems. Research laboratories, we have all fundamental shock tube and optical diagnostic measurements for turbulent flames. And then recently we have launched these big high pressure rig, which this is a kind of 2-story tall, the long high pressure pipe where we can elevate the pressure up to 40 bar condition. So modern combustion systems are anticipated to run on high pressure conditions. So we are able to place the actual burner inside this high pressure rig and have with the full optical access. And that's gonna be a very, this is actually serves as a user facility, so we are inviting many international group of researchers to bring their burners to the high pressure rig, for example, and you can take some experimental measurement. Engine activity is also growing. We have a couple of test cells, but we are also expanding a whole new building where about 11 new engine test cells will be placed. We have heavy duty, light duty, optical, and metal engines, multi-cylinder, single cylinder, all sorts of combinations to explore the modern engine concepts. So lastly, I would like to invite all the potential undergraduate PhD, the master's students to spend some time to experience what it's like to work at KAUST. We offer a lot of these internship program. That offers typically like 3 to 6 months, and we provide all the expenses, and you will be involved in one of the research laboratories with us and engage in the research activities. So if you have any questions, you can feel free to email me or any other faculty members of your interest. So switching to my group, I have a fairly big group now. So these are all my students and postdocs. Again, even my group alone covers more than a dozen countries. So it's a highly diverse group of people. And like I said, I'm the only one working on computational modeling in CCRC. So I cover modeling at various scales, all the way from DNS to device level engine simulation. Each of these applications, I use different tools. So I'm going to talk about DNS, focus on DNS today, but I also do open foam based large engine simulation that is directly compared against the jet flames experiment that we are taking measurement in our high pressure rig. And as for the engine, we have a long collaboration with Saudi Aramco. They are sponsoring all the fuels and engine research. So I do a lot of this multi-scale simulation all the way from neo-nozzle Eulerian simulation for a spray pattern to predict flashing, non-flashing sprays. And LES, recent development, LES simulation is valid against the spray chamber experiment. And then also full cycle engine simulation directly compared against the optical engine. So it's a full package by itself, but I don't have time. This is more like a specific application-oriented topic, and this is not of general interest at IIT Kanpur. So today I'm going to focus on my recent development on the DNS simulation, a fairly fundamental work, but is also relevant to many combustion devices such as IC engines. So I would like to give more credit to primarily my postdoc, Minbao Long. He did all the actual simulation work and analysis, and also my other PhD student and research scientists, they all involved in development of the code. Professor Bengt Johansen is an engine expert, as many of you may know, and we work closely together on this very topic. So he is also working on experimental part of that optical engine to measure the knock event. I would like to also acknowledge the financial sponsorship by KAUST in various formats, as well as Saudi Aramco fuel comp project. Computing resources are provided by supercomputers. I will show you some ridiculously large-scale simulation that is conducted by KAUST supercomputing facilities. So these are the engine knock. Not exactly inside the engine, but it's a more like optical device, you know, the cylinder-like situation. That experimentally, this knock detonation development has long attracted the combustion research. The fundamental mechanism of how, normally engine knock is one typical practical example. We all know what knock is. We just don't know exactly, even today, how the knock is developed out of some hotspot premature ignition, and that is developing into the knock. In these two contrasting videos, you already appreciate the complexity of the knock event. In the left side, you see that the hotspot is always on the left. It is developing the wave, and that shoots off the acoustic front that reflects off the wall, and then it takes a little while to develop the detonation. On the other hand, a little bit more of a O2 enriched condition, reactants are much more reactive, and you will see there is a spontaneous development immediately after, even before the wave front reaches the wall. You have spontaneous detonation transition. So this kind of contrast highlights the key theme of what I'm going to talk about in the subsequent slides. I'm going to reproduce this event computationally. So in terms of these two contrasting situations, can be easily represented by 1D scenario. So we will mimic the initial triggering of the onset of ignition by some temperature hotspot in the middle. These are solid walls, and you are having these pressure waves and temperature peak moving one side to the other. So depending on the mixture reactivity, when the temperature is a little lower, you will see it takes a little longer, and the ignition spot will develop the deflagration front, as you can see. So the pressure is blue, it's still low, and it takes a few more reflections and interactions of the acoustic front until, boom, you shoot up this detonation front. On the other hand here, the mixture is initially reactive enough, so you will immediately transition to the detonation. So those are two typical scenarios that we understand. But how this all pan out in a multidimensional complex situation in the presence of turbulent eddies and mixture stratification, that's a big fundamental question. So that's the main topic. So there have been already a lot of work done, and well-known Bradley's regime theory classified the detonation development very well. Basically, he classified the conditions into two key parameters. First is a C parameter, which is a ratio between speed of sound to the spontaneous front, which is a propagation speed of the ignition front. It's not necessarily a deflagration speed, but it's a general reaction front speed. The other one is a resonance time ratio, which is about acoustic time scale, which is R over A is a speed acoustic time scale within any the length scale of the hotspot. And I will elaborate more on that later. And relative to the excitation time. So in a nutshell, what we are referring to is ignition happens, and there's a heat release generated within the hotspot. And then acoustic front is propagating out. You want to make sure this heat release is rapid enough to catch up and interact with this acoustic pressure wave. And that's the basic recipe to develop the detonation. And that much we know. And we want to understand how that kind of a categorization in the one-dimensional model, and they predicted that the C value has to be in that range to develop the detonation, of which epsilon parameter, you have to have excitation time fast enough so that you fall into this range to develop the detonation. So that's a kind of a established theory, and we are trying to extend it into multidimensional simulation realization like that. So we just recently finished the 3D runs, which takes up many tens of millions of CPU hours, for which I'm using my own in-house DNS code. It's named CARFS, Chaos Adaptive Reacting Flow Solver. It's called adaptive in the context of it is adaptive in different hardware architecture. Modern supercomputer comes in hybrid of GPU and CPU, and our code is adaptable to maximize the code efficiency. It is basically well-structured finite difference code with extremely high order to preserve accuracy with the minimal resolution. And it is coupled to open source Cantera for chemical kinetic. And then now we have both operator splitting to handle stiff chemistry using implicit time integration. So this is 2D. We have conducted many cases of these 2D runs. And you can see with the WeKnow scheme, the shock capturing scheme we implemented, we are able to successfully capture these starting from the onset. What you are seeing, by the way, here is we impose a random temperature field as an initial condition without turbulence at this condition. And then we'll see how the hot spots grow, develop the front. And you can clearly see the contrast between the initial slow deflagration wave, and the moment you detonate, the detonation front is moving much, much faster. And that just swallows all the remaining, the reactants in the field. So that's the physics we are dealing with. It's still a miniature scale, barely like a few millimeter by a few millimeter size, but it still captures the essential details that allows us to investigate. These are very expensive calculations, like I said. Each day, the single run generates many terabytes of data, and a few million to 100 million hours in some of these big 3D simulations. It's extremely high resolution DNS. So how do we analyze the diagnostic to tell the tendency of the knock? So again, we introduced a predictive. So basic idea is that we want to predict it based on the initial field. Based on this C parameter, which was proposed by Bradley, as well as epsilon. I'll elaborate more on that in the next slide. So epsilon is another time scale ratio. Those are the two key parameters, and that is distributed randomly in the field. We will take the volume average, and that gives us some idea about how likely you will detonate subsequently. And these are the final effect. How that overall we monitor the volume fraction of the heat release at which pressure is much higher than equilibrium. So this is called FH. If the pressure is even higher than Chapman-Jouguet detonation pressure, we call it CJ. And then ZND, finally, that is the highest peak von Neumann ZND pressure. So, well, those are all correlated. You can expect that basically the FH is larger fraction, of which some subset of them will be even higher pressure range, and so on. So the initial distribution will lead to different tendency. And finally, we are recently started to working on the other aspects of the time scale ratio according to the Peters theory. He called it a dissipation element. Simply put, the dissipation element is a kind of length scale that connects a single flame, the temperature structure. If you have the fluctuating temperature front, that's the kind of scale we are looking at. So on the average, statistical average scale, you can refer it to be the Taylor microscale in homogeneous turbulence. So that is our dissipation element length scale. Based on, according to that, we can develop this epsilon parameter based on excitation time relative to this dissipation element length scale. So basically, the idea is the length scale of dissipation element determines the time scale of the acoustic wave to travel within that distance. And that time scale must be larger than the heat release excitation time in order to develop the detonation. So we expect the epsilon to be larger to promote detonation behavior in our statistical average of the random field. So that's basically the gist of the study we are testing out. So we tried many different turbulence spectrum sizes and intensities. Initially, we try temperature only without turbulence flow. And you can also, again, appreciate it when the epsilon parameter is relatively small, where the temperature gets actually, the heat release is not catching up fast enough, then you're not going to see a whole lot of detonation wave until everything gets burned. On the other hand, when the length scale gets larger, relatively larger, then you have more sufficient time to develop this heat release to catch up, interact with the acoustics, so you can clearly see the large presence of the detonation front. So qualitatively, we already clearly demonstrate those tendency is true. So that is actually, so even for the same statistical distribution of the C, which is the first axis of vertical axis, you can achieve the same C, which is only about the speed ratio. That can be achieved at different length scale and fluctuation size. The key findings we report is that basically for the same level of fluctuation, small scale gets washed out much quicker because of the mixing and diffusion. So they are less likely detonate. We'd prefer to have a somewhat bigger scale bulge while the bulk of the mixture is highly reactive, and that's more likely scenario that the hotspot will evolve into the detonation more easily. So that trend has been, so we compare the prediction metric against the actual observation metric. It's not perfect, but they've roughly, for many different parametric conditions, they roughly lie on the 45-degree curve, straight line. Although, once again, we confirm that one parameter, C, based on Bradley theory, doesn't really correlate that everything together. As you can see, for the same volume average C parameter, you will find totally different detonation intensity depending on the other length scale condition. So again, the whole this effort, it's been published, a few papers are coming out now. Main theme we are trying to report to the community is that there is a more complex story behind the full understanding of the detonation, in such that one of the focal quantity is the length scale of this turbulence mixing. Once you start introducing the effects of turbulence, now we are dealing with competition between two length scales. First is the length scale of the temperature fluctuation and the length scale of the turbulent eddies, and they don't have to coincide each other. So that is another experiment we've been doing. So you will appreciate these very, very complex, with the help of extra turbulent eddies at different size. This one is 5 millimeter of the length scale. So that's about the same 1-to-1 ratio between the length scale with the 1-to-1 ratio between the turbulent eddy turnover time against the overall ignition delay time. And that will create, still, its length scale is large enough, so it's almost like a frozen field. You will see those detonation takes off and just swallow all the remaining mixture field, which is much more reduced as the length scale gets smaller. So this is another contrasting view. When you're with the same initial size of the temperature field, but the turbulent eddies are much smaller. So like I said earlier, it will just wash away any of these hills and troughs of the temperature field. So you kind of homogenize while they're burning, and you're not going to find a whole lot of detonation development. So that's a key message. So the ratio, we argue that the ratio between those two length scale is a key parameter to be investigated when you want to predict the nature of the detonation and the likelihood of the detonation. So you could kind of see, depending on, I don't have time to explain which case is what, but in that direction of the tendency, you will see the ZND fraction, the burning at which pressure is higher than ZND is much higher, but as you increase the turbulence intensity, you tend to reduce down. There are some situations, special situations where you can expect to see turbulence can actually promote knock intensity, which is when the length scale gets bigger. So that is kind of, I already demonstrated. And we have also shown that with the same level of intensity by increasing the eddy size of the turbulent fluctuation, you can actually increase the peak pressure level much higher. So these are done by the dozens of the 2D simulation, each of which takes about 1 million hour runs. And so these are some examples how that turbulence can impact. You can see those, while it's rapidly mixing, it still preserves some of these mean gradients of the temperature that allows this detonation development more easily. So this is a work in progress. I just wanted to impress you with this massive 3D simulation with one case with low turbulence. You will see that this one, again, eddy turnover time is on the order of the ignition delay time. So by the time the detonation happens, you will see it from the kind of a gray to red color in the pressure map. You will see the detonation structure is a lot more scattered. On the other hand, if I have a high turbulent intensity at the large length scale, you will be able to kind of mix up the radical generation. And by the time detonation happens, you will see the much bigger unit of the detonation front. You will see a lot more vigorous detonation phenomena when the eddy turnover time gets much reduced. So we are still analyzing the data to get more meaningful answer to our questions. And that's kind of value of this high fidelity DNS simulation in our fundamental understanding. Finally, our current work in progress. These are, again, what we are trying to do is, if I give you the initial profile, temperature field, pressure field, mixture composition, or even some derived quantity like those C epsilon parameters, I can compute it in advance, and I have hundreds of those data, and I run the simulation, I know the answer eventually. So can I predict it by machine learning? I think this is a very nice exercise we can do. So this work just started with the help of some machine learning expert. So this is almost like image capturing by the machine and AI. So that's the kind of work in progress. With here we are introducing the definition of the dissipation element. So this kind of work will allow us to identify what is the best predictive metric to predict the knocking tendency with the highest accuracy. So that's the further work in progress. We have plenty of data already accumulated to work on that. So with that, I would like to summarize. Again, the message here is that Bradley theory has been around for decades already, but it still doesn't provide the whole picture. We have reported in our series of work that the length scale ratio between temperature and turbulent eddy size plays a crucial role. Sometimes, depending on that condition, turbulence can suppress detonation, or sometimes it can promote the detonation. So though we need to further rationalize and identify the key characteristic parameters. This still doesn't tell us whole story. Our simulation domain size is relatively small. In a real world engine knock, it is an action of the interaction between multiple waves. We kind of capture that in 2D, 3D simulations, but how that exact shock-shock interactions, especially in a 3D context, plays a role in the ultimate fate of detonation development, that is really a profound question that requires further study. So with that, that's all I have to say. Thank you for your attention. I'd be happy to answer your questions.
So, any questions?
Hello. My name is Kunveer. I'm from Mechanical Engineering Department here at IIT Kanpur. Since you talked about different time scales involved in such kind of simulations, so can you comment on the role of the choice of chemical mechanism for such predictions?
Oh, okay.
Because since the ignition delay time is highly dependent on the type of chemical scheme which we are working with.
Yeah, absolutely.
Yeah.
Well, so to me, at this type of predictive theory, honestly, the only thing that in the ballpark estimate, the only thing that matters is ignition delay time. So right now, we have mostly worked on the hydrogen fuel and some other non-NTC fuel. So for whatever detailed chemistry I have, as I put it in, I know the ignition delay time as a function of temperature. So that curve is primarily that dictates the C parameter to begin with. So that is clear. What would be very interesting is now if we start talking about engine-like complex fields where you can see those ignition delay time curve shows a negative coefficient behavior. That's when things becomes very interesting. So we have done some preliminary work on that in a phenomenological behavior earlier. So simply put, if you have, basically it's a gradient. So when I have ignition delay time, more sensitive to temperature, if you think about it, as I have more fluctuation in temperature field, you will see a bigger impact to the ignition delay difference. So that ends up promoting more into the deflagrative mode of the propagation. The detonation requires a faster propagation, so it prefers a shallower, so lower ignition delay sensitivity. So it is a combination of your chemistry in that how sensitive is your ignition to your mixture condition, and then what exactly is the actual condition. It's a combination of both, and that's basically the name of the game here.
So do we need some a priori reaction sensitivity study for this before running a...
Yes, well, we have a 0D data, of course, for the kinetic mechanism. So we know what to expect. So that's the baseline. And if you, so that, well, the idea is that non-dimensional number will tell you that. And if you try out different, n-heptane fuel later on, as I get that curve, 0D homogeneous curve, then this parameter will still give you a good prediction for the knocking tendency. That's the idea.
Thank you.
There's one more question at the back.
I'll let you
Hello.
enjoy the 3D movies.
Yeah, very nice talk. I'm Amrish Khut from Cummins. So my question is, so you have simulated the DNS, so where we can say at any corner or any section or any point resemble the same physics throughout the cylinder. So whatever you have shown is within the core of engine, or it is in any particular wall?
Well, this is a periodic box at the moment, so which means it's kind of wall. So pressure keeps rising. It's like constant volume ignition phenomena. So that's why I meant by engine-like condition. So you can think of it as a small subsection of inside the engine near the top dead center. So pressure is set up that way. So it's roughly, you can see that it's a low pressure is like a 4 megapascal. It's a 40 bar condition.
Yeah,
so
and how you derive the boundary conditions for that particular section? Is there any?
Well, these are periodic, so that's the easiest you can think of. So what goes out comes back in, X, Y, Z direction.
And what is the section size, cell size?
So these are roughly order of like a few millimeters to a centimeter long. So it's like it's a very small.
Okay. And do you have any plan to simulate entire cylinder?
Well, not with DNS, unlikely.
Okay.
So the idea is that with this DNS, just like any other turbulent combustion research, the fully resolved DNS is a subset of a real system. And by processing the data, we get an idea. My hope is eventually derive the DNS validated predictive tool and use it for, if you're gonna do the engine runs, it's most likely be a RANS simulation.
Right.
So RANS will give me some average data information. Can I use that information, such as the Taylor microscale that I can get from the RANS K epsilon quantity? And does it work? That's basically the ultimate practical question.
Okay, so this will be the model calibration study mostly.
It's more like a priori study based on fully resolved data.
Yeah, thank you.
Thank you.
One more question.
Good evening, sir. I must appreciate the scale of work. So I want to, because I am mostly on nanotechnology and I am working on microwave irradiation. So there is a concept of localized heating in case of microwave irradiation when we deposit films. So what if in this system means like when we consider these systems, do we neglect that electromagnetic radiation or anything like that?
Well, not unless you actually impose it. Yeah, I understand microwave and even plasma. Those are considered viable ways to ignite the combustion in the engine. So that is but spontaneously generated electric field, ions generation. Every flame generates ion by itself. But normally the chemi-ionization, that effect is not big enough to make any big difference unless you actually impose it. I'm also working on that topic as well. So what if you put some electric field to the flame, and flame actually responds due to these electromagnetic forces.
So in future, if I want to fail these IC engines that basically people have already discussed about, then I will just use 3 or 4 magnetrons with different frequencies. Basically, I will use ISM band because that are free. And I will superimpose them and I can easily fail the IC system designed by the scientist or
So, sorry, if I understand correctly, you are talking about microwave generated spark.
Yeah. For
right?
example, I have a magnetron and I just keep superimposing different electromagnetic radiation, and I reach an amplitude and a frequency so that it is enough that can generate a high impact at a particular point, say impact.
Okay, so is it localized?
Yeah.
So that's more like ignition spark. Again, the whole thing I'm talking about is not about ignition. I am assuming there is in the mixture, highly reactive mixture, will have some hot spot. It could be metal particle, oil residue, or maybe a laser sheet pointing at certain location. So you'll initiate the ignition. And normally you don't want that to, well, that's how you start the flame. And under normal condition, you'd rather have the flame front propagate, sweep through the mixture without knocking, without detonation. So, but detonation is becoming very important topic in the modern engines because in favor of efficiency, we want to boost and higher compression ratio. So even the mixture gets very reactive even during the compression process. So even before you start the spark, it can ignite due to the action of these metal particle impurities. So that's called the pre-ignition, and sometimes it can lead to super knock. So that's another. Engine knock is a conventional, the after ignition knocking event. Pre-ignition is another new problems of the modern engine with the boosted operation.
So that part of study has neglected that part, means or not included that part of electromagnetic radiation.
Yeah.
But that can be a possible danger in future,
right,
when we do not consider that part.
So how, like I said, however you initiate it, ignition, depending on the bulk mixture condition, how reactive they are, how stratified they are, you can have this knock while they're burning. So this is what we don't want to see inside the engine, because once in 1,000 cycles, if you have once in that event, your engine is gone. So this is a really very important industrial topic.
Are there any more questions?
Thank you, sir.
Thank you.
From the audience? Well, hearing done, let's give our speaker a big round.
Thank you very much.